Starting with a short Miley for today's class, we had studied yesterday that how we can obtain amplitude resonance by varying the frequency of the forced oscillator, and how we can obtain velocity resonance also by varying the energy resonance by varying the frequency of a forced oscillator. Here we had started off with the real component of the externally applied periodic force, which is cos omega t, and the displacement, the real component of displacement. And we have seen that the total phase difference comes out to be minus of phi plus pi by 2. The amplitude for displacement, as you see, is f0 omega by zm. So you see, if you try with the imaginary component, as I told you yesterday, you will be getting the same result. And if you just simplify this a little bit, okay, by putting the value of Zm, you actually have to do the simplification over Zm. Then, well, you can show that Zm is equal to this. You have to make a substitution of 2k for r by m and omega 0 for s by m, so that for y you get this ultimately. And if you take f0, capital F0 by m as f0, okay, so f0 is equal to f0 by m. If you take that, then you ultimately from here, and if these two omegas will cancel, they will cancel, then you get this as your ultimate result, which you need to remember to explain this very important part of forced vibration. Okay, now you see over here, well, this is your tan phi. Okay, so s by omega. So if you omega m minus s by omega divided by r. Okay, so you can write tan phi in this manner. Alright, and therefore you can take out the amplitude which we observed yesterday, which is also, as I keep on saying, very important to discuss the various cases of variation of frequency, like this. Okay, so ultimately this is the factor which you need to remember, which you need to discuss for your various variations of frequency in forced vibration. Okay, now the different cases: low frequency, high frequency, and when omega is equal to omega naught. So at low frequency, the amplitude depends on just the amplitude of the driving force and stiffness constant, and it has no omega dependence. Realize that. Case 2, well, it depends on the frequency f0. Okay, and for very low damping constant, it is f0 by omega square, such that because it is f0 by omega square, at high frequency, if you make the frequency very high of your forced oscillator of the externally driving periodic force, then amplitude goes to 0. And when you make omega equal to omega naught, I repeat, this is the case which we discuss, which you get in your exam, you get amplitude resonance, which gives the value of the amplitude as this. So if you put down the value of the amplitude A in this manner, then substitute, you can show that, well, for what value of omega would you get the amplitude resonance, you can find out if you do dA d omega equal to 0. You will see that for omega square equal to omega 0 square minus 2k square, where omega 0 is your natural frequency. This is your natural frequency. Okay, and this is the frequency of your forced oscillator. Alright, so, and the overall frequency of vibration that occurs. Okay, So then you get omega square as equal to omega 0 square minus 2k square. If you do this differentiation, thereby getting omega as this. This can be simplified in this manner, and you need to remember this because of your problems, because if given the damping constant, mass and the natural frequency, you have to calculate, suppose say omega, then you have to do this kind of a problem. And this is how the amplitude resonance graph goes. If you plot it versus displacement, you can show that here the displacement, it increases, reaches a maximum and then decreases after a certain point. And this amplitude, maximum amplitude, occurs for different values of damping. Okay, R1 greater than R2, that means if your damping is large, you get lower values. If your damping is high, if your damping is small, you get sharp higher values of amplitude for amplitude resonance. Similarly, when we work on the velocity, if we work on the velocity of a forced oscillator, what is our observation? Well, again, starting from the same master equation, if this is the real part which you take, then velocity is dy dt, and ultimately what you get is v is equal to v0 sine of omega t minus phi plus pi by 2. So if you compare the phases of v with y, you see v leads by pi by 2. Same thing you can see for your, if you compare it with your driving force. Okay, if you compare it with your driving force also, you will see that here also the velocity, if you just make a comparison with f, you will see that it lags by phi. Okay, now over here the amplitude of the velocity is f0 by zm, and so again, as I keep on repeating, if you remember this formula for zm, okay, if you do the calculation for low frequency, you will see the velocity goes to 0. Okay, if you do it for high frequency, you will see then also the velocity goes to 0. And at resonant frequency, you will see when omega is equal to omega naught, you will see Zm is equal to R. So ultimately you get F0 by R. Again, therefore, when R is small, as you see the amplitude, as you see, if R is small, the amplitude of velocity is very, very sharp. Okay, a bit of a reflection in this diagram. So this is what you see over here. You all you have to do over here is to get omega equal to omega naught, the condition for velocity resonance. You have to do dzm d omega equal to 0. So it's pretty sharp. Okay, for low values of damping. Okay, so if this is your R1 and this is your R2, R1 greater R1, this is your R1, and if this is your R2, R1 is greater than R2. So this is quite flat. If you keep on increasing damping, sharpness becomes flat. Okay, so with this knowledge, let us study today the variation of phase, because that was the question I gave you in MCQ yesterday with velocity. Okay, of a forced oscillator. So let's stop over here. So much so for the Miley for today.